My name is Ruslan Gleiben. I'm doing Raspberry Pi Lab number 3. Okay, so this is the code from Lab 3, main.s, and this is the code GPIO.s, which we use to compile a program for the blinking LED. So in the main.s file, we use the global directives assembler, and then we use the branch actual main code, which is the part that just assembles the thing pretty much. So in the beginning we use this code which says move stack pointer. We're gonna use stack pointer to 8,000, and the pin number will be register 0, as given to us with it's gonna be an alias pin number, and registry 1 will be an alias pin number function. So we move the pin number 16. We give so it's gonna do the value of 16 for LED light. Then we move the pin function 1. It's gonna give us the value of 1, the output. So we set the GPIO function as a call function, and unrec means to delete the pin number and delete the pin function. Basically, it's an alias for delete. So we will create the delay for the busy processor to decrement the number of this address to 0, and we're decrementing the alias to 0. So we decrement the register to 0, and move decrement registry for this value, which is it's going to decrement value for how long the light will be on, and then decreases the value by 1. Then the test if decreasant equals 0, then not the test, the tech decrement 0, which is equals to 0, and the BNE will wait. If not 0, then it will do it again. If 0, then it'll go to the next, and then it will delete again that decrementation. So it deletes as an alias again. So the pin number is 0. It's given to us as an alias number again, and the pin value is 1, so it gives us the same as in the beginning. We had the same pretty much thing, and then we move the pin 16, which is given to us to a value of 16, and then we move the pin value to 1, which is in set GPIO to pass the set bit to 28, and then we turn the pin on, and the light turns off, basically. So we again delete the alias, delete the pin value, and now we're gonna decrement the registry 0. The alias is gonna be R0 registry is decremented, and then we move the decrementation to address 03F000, and then this will be how long the light will be off. Yeah, similar to this one, but this one's on. This one will be off, and then we wait again, and it will be sub decrement value by 1. If the decrement 0 test is equals to 0, if not, then not 0, then do again. If 0, go to the next, and it will delete the alias again, basically, of this this command, and then it will loop over the process forever more. Basically, it will just keep on blinking non-stop. Go to GPIO. This comes from the author Alex Chadwick, and the GPIO.s is more of a similar way, but it's a little bit different code. So I'm gonna take it's gonna return the base address to physical address in registry 0, and then takes no inputs to return GPIO address, and then global uses global to get GPIO address. Makes label name, so it's gonna be accessible to all files which are able to branch here from main.s, even though it's not defined there. And we first in our GPIO so we first get GPIO address loader. We load registry 0, which is this address right here, and then we store the GPIO control in address registry 0. Then we move the loader and then copies this address 0 to 0 0 0 0 0 into the program counter. Now we set the GPIO function set and sets the function of the GPIO register addressed by registry 0 to load 3 bits of registry 1. So we're gonna use the C++ similar code, which is set GPIO function 32 GPIO registry, and then universal 32 function for these two. So we're gonna set global GPIO function, makes the label again, which is for manually setting the pin 16 that can be used to set any pin, not just the LED, which is defined in main.s file. Now we compare the registry 0, which is 53 pins, with 53. So it compares registry 0 with 53, and there are only 54 GPIO pins from 0 to 53. And then it does the registry 1 to, compares with 7. So basically it compares from registry 0 to 53. If it's slower or equal to 53, then it compares to registry 1 with 7 to make sure that registry 1 is one of the 8 functions pins that can perform from 0 to 7. Now we move high for the program counter. LR means to return address. The return address input, so it does not run if both conditions met. Does run if either and not met higher than 53 or 7, basically. So I'm gonna push return address, which copies the value in return address to the top of the stack currently in registry 0. If above condition met, and then we move registry 2 to registry 0, move GPIO address from registry 0 to registry 2 to ensure it's not overwritten, and then the get GPIO address returns GPIO address again, and then GPIO functions are stored in blocks of 10. So we have to determine which block our pin number is. So the function loop is, we'll compare register 2 with number 9, pin number 9 to 9, and then we sub high register 2 with pin, we basically, if higher than 9, we subtract 10 from the pin number, and then we add high, which is register 0 adds, that's why we add 4 to GPIO controller, and the functions loop again, be high runs again. So it does GPIO controller equivalent to GPIO and the controller address plus 4 times GPIO pin divided by 10. So we add register 2. Register 2 becomes then the multiplication by 3. So we do register 2 times 2 plus R2. And then we also do shift left function and the value by register of 2, and then this, register 1 and register 0 stores in the computer function, which is a value address in GPIO controller, and then we pop. We delete program counter from the stack, value copied to the return address, which returns the function. And then we set the function, the GPIO pin address by register 0 high if R1 is not equal to 0, then we, and low otherwise. If value 0 is off, LED is off, anything else on. And the global set GPIO is set for to make function accessible from other files. So we're going to use pin number 0, register 0 and register 1 pin value. So register alias allows the names other than R0 and pin number R0, other than R1 and pin value R1. So there, I guess the input and output is similar. So now it compares the pin number 53. So it compares the register 0 with 53, and there are only 54 pins in GPIO from 0 to 53. So we move high and return if R0 is greater than 53. Okay, so we push return address onto the stack, and then we move the register 2 pin number, move the contents from register 0 to register 2 to ensure if they are not changed. Then it deletes the pin number from register 0, and then deletes the register 2. Wait, no, not register 2. It gives the alias number to register 2, alias number, pin number to register 0, and we get the address called get GPIO function. So the GPIO address required is R0 to reflect the function call, and pin bank register 3 gives alias 3, register 3 alias. Now we do shift to the right. So device number sets off. GPIO has two sets of. So we have 4 bytes to turn the pins on and off, which is 32 and 22, and then it determines if it which is and it is in. So 2 to the 5th is 32. So shift left pin bank equals 2. So we shift 4 bytes multiplied by 4. The GPIO now contains the address 02202000 if the number is from 0 to 31, and if the pin number is 32 to 53, and then we add the pin bank. If 28 base 10, then is added pin is on, and 40 base 10 pin is off. So we remove the pin bank, and now we just go into pin number 31, which remainder the pin number divided by 32, always between 0 and 31. So we set the bit number to 1, give the bit number a value of 1, and now test if the pin value equals 0, and then we set the bit address to 40, number 40. If pin value equals 0, and then we'll store 1 bit at 40 away from the GPIO, will turn off. It turns off the pin and off, so the light will turn on. And then the same thing for the second line. If it's 28 and the pin number is not equals to 0, it will set the bit to 1, but at 28 away from GPIO, turns on the pin, but the light turns off. So unrecognized the set bit gets deleted again, and the GPIO address gets deleted again, and then we pop the program counter, sets the value of program counter back to the value of the return address. So now I'm gonna run the CMD file, command prompt. Let me go into my Egardo tool. Egardo tool into my disk C. Make sure everything's deleted. Do make clean. Oops, okay, never mind. Forget that I need to put in my command thing, and it's gonna be Egardo /bin, and now I'm gonna put in my pymake clean. So it's gonna clean all the files that build basically. So it looks like it did clean all the files except the source file and a make file, which I want to delete these two. Okay, so I'm gonna go get the source file of the third one. get a new. Actually, this one's fine. Let's check if this one works. Okay, check if this one works. So we copy and paste it to the guard tool. Yes to all. Now the command, and we type in pymake. Oh, something's conflicting it. I have to do pyclean again. 1 minute. Pyclean. Pymake. Clean. Solana. So I'm gonna go into my computer organization folder and get the third one unzipped again. Extract. Cut. Paste it back to my. Sorry for wasting my time. Okay. And I'm gonna go and copy those files again. Copy the source folder, put into the source folder, goes into bin. Yes to all. So now we're gonna run command again. So pymake. So we got that. Now we highlight mark. We get the second file, copy, paste, and then press enter, and do pymake again. We get the error, so I'm gonna just copy and paste my make file. Okay, now let's do pymake again. Okay, so generate the image. Now I'll take this image right here and then send to G drive. Say yes, and that's it. I'll make another video that will show the demo of the Pi blinking. Thanks. Goodbye. Thank you for watching my video. Bye.